Hi, hello, my name is Alvin Orbach White. I'm going to give a brief introduction to the Reynolds number now. You can reach me at any time at this email address at alvi@mit.edu should you wish to contact me. I've chosen the Reynolds number essentially because it's one of the most important values in fluid dynamics and fluid mechanics. By understanding the Reynolds number or by evaluating what the Reynolds number is, you can very quickly understand what the dynamics of the fluid is going to be like and what kind of properties will be associated with your processes or any processes in question. If you look around you, we are immersed in fluid all the time. Yeah, there's gases moving about all the time, and in order for chemistry to happen, gases have to meet each other, or even liquids have to meet each other, and liquids and solids have to meet each other, and they have to mix around. They have to have some kind of turbulence in order to turn and come into contact with each other. Okay, let me give a little bit of historical context. The Reynolds number is named after a man named Osborne Reynolds. He was a Belfast-born scientist who was investigating how water was flowing through pipes. Okay, in 1883, he popularized the idea of the Reynolds number, which is named after him, because he was noticing that under certain conditions, he was seeing the water was acting very turbulent, and in other conditions, he was seeing the water was acting more laminar, and so turned to coin these turbulent and laminar flows. He was able to use the mathematics to determine, calculate, and predict whether you're going to be in a turbulent or laminar regime based on certain physical parameters associated with your system. Those physical parameters being the velocity of your fluid, the density of your fluid, and the characteristic length upon which you're interested in observing your fluid, and also then the viscosity of your fluid. Now the top parts are associated with the inertial forces, remember velocity, density, and length, and the bottom part is associated with your viscous forces. So immediately you get a ratio between your inertial forces and your viscous forces. And depending on how large either of those are, you're going to get a larger or smaller number depending on the numerator or denominator, which is bigger. Okay? If you get a number closer to 0, you're in the laminar regime. As you get a number closer to 2,000 or 4,000, you're heading into the turbulent regime. Okay? So you never have an exact one or the other. You're always going to have some kind of interstitial state in between them. So it really gives you first-hand understanding of whether you're going to have a laminar or turbulent regime, and that's important for a lot of applications. So one way that we see this physically is we see the top here we have turbulent regime, and down here we have laminar regime. Turbulent regime, this is water mixing. This is actually water mixing in the Atlantic. There's warm water coming up from the Gulf of Mexico. It heads over to Western Europe, hits the shores of Ireland and Wales, and it heats up the water there, creates a lot of moisture in the air. You got a lot of rain. Okay, down here you got laminar flow, no mixture, no mixture. Background is white. The car is in front of all these gases. The gases don't mix with each other. They're streamlined. Okay, you see the streams are just moving in lines. So that gives you the idea of how streamlined the car is, or an automobile, for example. Also, Reynolds number is very often used in scaling laws, particularly for aerodynamics and hydrodynamics, and you can see exactly why here now. So you can have a small scale model, and then you can see how streamlined that model works, and then before you just build the actual car, you get a good idea for how to utilize it. Whereas up here you have a lot of gases mixing. You got red turning into blue, so this is all mixing around, and the water is changing temperature. Down here, no mixing, streamlined. And this is important for an application that I'm very interested in. I'm going to briefly introduce you to now, which is synthesis of carbon nanotubes. Essentially, the nanotubes are made in a horizontal quartz tube, which is essentially the similar situation that Osborne Reynolds was investigating. Now, in these particular reactions, the flow of gas is at a very, very low rate, so the inertial forces are very, very low, so the Reynolds number turns out to be very low too, 0.04, so we're very much in the laminar regime. So laminar regime, you can expect that the gases are just going to be flowing in these lamella, and when a nanotube is able to grow, if it gets into one of these slipstreams or one of these gases, it's just going to continue to grow. Okay, and in order to assist that, what I do is I put a little bit of an angle of attack on the substrate, and you get a little bit of a lift off, just like you get in a wing. And when you get that nanotube up into the lamella, it basically just floats down through the system. Okay, so here I got a SEM or montage of 400 SEM images, which is overlaid on an optical image just to show one tube, which is just over an inch in length. And the idea is to continue doing this work so that you can make longer and longer nanotubes. So I hope you get an understanding for the way that I like to teach my classes. I pull in information from textbooks and show how they're applied in the real world and also in research.